What if Einstein's problem with quantum mechanics could actually be tested, and the universe gave an answer that he probably would not have liked?
I mean, it's a terrifying thought for any physicist, honestly.
Right. Well, welcome to the deep dive. We are cracking open a 47-year scientific cold case today for you.
Mm-hmm.
It's less like a physics lecture and more like, I don't know, a high-stakes detective story about the actual nature of reality.
Yeah, it really is. And the evidence file we're looking at spans 3 massive breakthrough papers.
Over almost half a century, right?
Exactly. So we start in 1935 with Einstein, Podolsky, and Rosen,
Yeah.
then John Bell in 1964, and finally Alain Aspect and his colleagues in 1982.
Okay, so if you're listening, buckle up, because we are tracking a huge arc today. We're going from like a philosophical accusation to this brilliant mathematical trap and then ending in an actual real-world sting operation where nature is essentially forced to confess.
Forced to confess, yeah, I like that.
But to get to the sting, we have to start with the accusation. So 1935, Einstein and his colleagues published this paper. What is his actual problem with quantum mechanics? Because the math was working, wasn't it?
Oh, the math was working beautifully. It predicted experiments with just incredible accuracy. Their paper, which physicists usually just call the EPR paper, it doesn't argue that quantum mechanics predicts the wrong results.
Okay, then what's the issue?
The accusation is that quantum mechanics doesn't give a complete description of physical reality.
Wait, so Einstein isn't saying the math is broken, just that the blueprint of reality is missing half the pages.
Exactly. They felt something was being left out. And to prove that, they had to lay down a very strict rule for what reality even means. They called it the reality criterion.
The reality criterion.
Sounds intense.
It is. It basically says if you can predict a physical quantity with 100% certainty without disturbing the system in any way, then there is an element of physical reality corresponding to it. Okay, let's unpack this for you guys listening. I will use the simple analogy here. Imagine we have two separate boxes, box A and box B, right?
Right, and they've interacted in the past and then separated.
Yeah, so they fly apart. If I measure something about box A, and that instantly lets me predict something about box B without even touching box B, then whatever property box B has must be a real existing thing.
Yes, exactly, because you didn't touch box B to create that property, you just knew it.
Right.
So EPR used this idea with what we now call quantum entanglement. According to the quantum rules, if you measure the exact position of particle A, you instantly know the exact position of particle B.
Even if it's miles away.
Even if it's across the universe. And if you choose to measure particle A's momentum instead, you instantly know B's momentum.
Okay, so applying Einstein's rule here, box B's position is real, and its momentum is real, because we can predict either one without touching it.
But here is the trap. Quantum mechanics says that precise knowledge of one property precludes knowing the other. The math fundamentally says a particle cannot have an exact position and an exact momentum at the exact same time.
Oh, I see. So Einstein is saying, look, my rule proves the particle definitely has both, but your math says it can't have both.
Exactly. So EPR concludes that quantum mechanics must be missing something. It's incomplete. There has to be hidden information.
So if quantum mechanics is missing information, what is that missing info? Like, what was Einstein's escape route here?
The escape route is this very intuitive concept called local hidden variable.
Local hidden variables.
Okay. Basically, the particles aren't communicating with each other from far away. They just left their common source carrying pre-written instructions.
Oh, right. Like, I love this analogy. If two people leave a house and you see one of them walk out the front door wearing a left shoe, you instantly know the person walking out the back door has a right shoe.
Right, exactly.
The shoes aren't, telepathically communicating with each other across the house.
No telepathy needed.
They just left with a coordinated pair. The right shoe was always a right shoe, whether I looked at the left one or not.
Yes. If we connect this to the bigger picture, you can see why this was so appealing. It's elegant. It completely preserves our everyday, comforting view of the universe, where things just have definite properties. There's no spooky action at a distance, as Einstein called it.
It sounds so plausible. Honestly, it's just common sense. So for decades, this was just, two sides arguing philosophy, Einstein saying it's shoes, and quantum physicists saying, no, it's weird math. How do you even test a philosophy?
You couldn't for a long time, not until 1964 when a physicist named John Bell enters the picture.
Here's where it gets really interesting.
Yeah, John Bell does something truly incredible. He takes this philosophical dispute about shoes and hidden variables, and he converts it into a strict, testable mathematical challenge.
Okay, so how does he do that? Because hidden variables are well, hidden.
Right. But Bell realized that if these particles are just using pre-written instructions, there is a hard mathematical limit on how perfectly their measurements can correlate.
Wait, I want to use a game show analogy for this.
Uh,
Imagine two separated players, right? They're in soundproof booths.
okay, yeah.
They could agree on a strategy beforehand that's the pre-written instructions, the hidden variables, but they absolutely cannot communicate once the game actually begins.
Right, they are totally cut off.
So the host asks them random questions. Any strategy they agreed on, no matter how clever, places a strict mathematical limit on how often their answers can perfectly match up. They literally can't win every single time.
That's spot on.
Yeah.
Bell proved that any local hidden variable theory has this ceiling, this limit on correlations. But the crazy thing is, quantum mechanics predicts correlations that break past that limit.
Wait, what?
Yeah. Quantum mechanics says that if you run this game show, the particles will win more often than any pre-planned strategy could ever possibly allow.
So Bell basically proved that if quantum mechanics is fully correct, the comforting shoe explanation or the game show strategy is mathematically impossible.
Exactly. The pre-written instructions just cannot mathematically explain the quantum results. It's impossible.
That is mind-bending. But, the trap was drawn on a chalkboard in 1964. So someone actually had to build this game show in the real world to see who was right.
And that took a while. Fast forward to 1982, a French physicist named Alain Aspect, working with Jean Dalibard and Gérard Roger, decides to finally run the ultimate sting operation on reality.
But wait, didn't people try to test this before 1982?
Uh-huh.
Like in earlier tests where the machines were just sitting there? Couldn't the measuring devices have somehow, I don't know, whispered to each other at light speed and coordinated before the particles even arrived?
Yes. You've just hit on what physicists call the locality loophole.
Oh, so that was a real problem.
A huge problem. Because if the polarizers the device is asking the questions are fixed in place, there's theoretically enough time for a signal traveling at the speed of light to warn one device about what the other device is doing.
Right. They can cheat the game show.
Exactly. So to close that loophole, Aspect's setup had to be revolutionary. The key idea was you have to switch the polarizer settings while the photons are already flying through the air.
The photon is already on its way, flying through space, and then you change the question you're going to ask it.
Exactly. You change the settings so late that no signal, not even one traveling at the speed of light, could cross the room to warn the other side.
Okay, let's paint a picture of how ridiculously fast this is. In the source text, they used calcium atoms, right? Emitting pairs of photons.
Yes, they excited calcium atoms, which emit two entangled photons in opposite directions.
And what was the transit time? How long do they have to change the question?
The photons had a transit time from the source to the detectors of just 40 nanoseconds.
40 nanoseconds. 40 billionths of a second. You can't just have a guy flipping a physical switch that fast.
No, anything mechanical is way too slow. So Aspect and his team used an acousto-optical switch.
Wait, acousto-optical, like sound and light.
Yeah, they used ultrasonic standing waves in water running at 50 megahertz to change the path of the light.
Okay, so they blasted water with ultra-high frequency sound to make ripples, and the ripples acted like a microscopic mirror that flips back and forth.
Yes. Every 10 nanoseconds, the acoustic wave would change the optical property of the water, literally redirecting the flying photon to a completely different polarizer.
Wow. So the photon leaves, and 10 nanoseconds later, the track just switches.
Exactly. It completely closed the communication window. Nature had nowhere left to hide.
That is the most incredible high-tech sting operation I've ever heard of. So the trap springs. They run the experiment. What was the universe's answer? Who won the game show?
Quantum mechanics won. The observed correlations violated Bell's inequality by about 5 standard deviations.
5 standard deviations. That's not a fluke. That's a definitive slam dunk answer.
Yeah, it completely blew past the mathematical limit. It perfectly agreed with quantum mechanics. Local hidden variables were basically ruled out.
So they weren't using pre-written instructions. They were literally communicating. Wait, does this mean they're talking to each other faster than light? Doesn't that break, like, all of physics?
Well, what's fascinating here is a crucial nuance straight from the paper. This does not allow faster-than-light communication for us.
What do you mean, for us?
I mean, you can't use this connection to send a message. When you measure your photon, the result you get, whether it's up, down, left, right, is completely random.
Oh, I see.
Because you can't control the outcome on your end, you can't tap out a message in Morse code to the other side. The connection is there, but nature permanently locks you out of using it as a telephone.
That is so eerie. It's like the universe is doing it, but making sure we can never weaponize it.
Exactly. Now, I should add one caveat, because science is rigorous. Aspect acknowledged in the paper that the ultrasonic switching they used was quasi-periodic rather than perfectly purely random.
Quasi-periodic meaning it had a rhythm to it.
Yeah, it oscillated predictably. So a super stubborn skeptic could argue, well, maybe the machines could still guess the pattern. So it wasn't the absolute final 100% loophole-free test.
But it was basically the nail in the coffin.
It was a massive, historic blow to local hidden variables.
So what does this all mean for us? For you listening? Because honestly, my brain is kind of melting. Do we just say, oh, well, Einstein was a dummy, he was wrong?
No, definitely not. That is not the takeaway here. Einstein brilliantly identified the flaw in our understanding. He asked the hard question. And because he asked it, Bell found a way to interrogate nature, and Aspect built the machine to do it.
Right, it's a chain reaction of genius.
And Aspect showed that the straightforward idea of locality combined with predetermined hidden properties, it simply cannot reproduce reality's quantum correlations.
The shoe analogy is dead.
It's dead. The unsettling truth isn't just that particles are secretly sending messages, it's that our everyday picture of separate objects carrying independent local properties, it may be completely inadequate.
That is so wild. Like, our fundamental assumption that a thing over here is completely independent of a thing over there is just false at the lowest level of reality.
Yeah. The universe is deeply, fundamentally entangled.
Well, I want to leave you guys with a final provocative thought to chew on today. If no ordinary local hidden story can explain these correlations if there are no pre-written instructions, what does that tell us about reality before we measure it? Does it even exist in a solid state, or is it waiting for us to look?
It's the ultimate question, isn't it?
It really is. Listen, if you found this journey into quantum weirdness interesting, please like the video and subscribe for more stories where science gets stranger the deeper we look. See you next time.